Start with our previous discussion. As in the last lecture, I have given you the overview of our next module. Our next module is time domain and frequency domain analysis of network circuit. In frequency domain analysis, in the sense like as I have already told you, as we were doing in our first module, we were also at that time we were also doing that analysis in the sense we want to find current and voltage in some particular branches, in some particular components. Like it could be voltage across resistor, it could be voltage across any element, other element, it could be your power element, it could be any of it. That is your analysis. So in this module, what's the difference? The difference is now we will try to analyze our circuit with having inductors and capacitor. Earlier we were discussing there was only resistor, and we will see that the property of resistor is very simple. It's like it is not having any problem to flow in current itself. Like if we are talking about inductor and capacitor, we'll see that they doesn't allow sudden change across it. Okay, so we will start with our discussion with the circuit elements. As in the first module, I have told you about only resistors. We haven't discussed about inductor and capacitor. So let's start our discussion with inductor and capacitor in little more detail. In case of resistor, the voltage across this resistor was, if this was the positive terminal and this was the negative terminal of this element, then the current across it is suppose I and voltage is V. Then this voltage is given by I into I. I know everyone knows about it. So now let's see what was the case of inductor. As even we had seen about inductor, that the voltage across inductor is suppose V and current across this is I, and suppose the value of this inductance is L, then in that case the voltage across this inductor was, you all know, that is nothing but L di by dt. And in the case of capacitor, the voltage is given by, as if suppose V is this and current flowing through it is I, then in this case the voltage across this capacitor is given by 1 by C times integration of minus infinity to T I dt. Okay, so now if we talk about the current, then current in the resistor is having no problem, like your current will be given by V by R. That's very simple. And if we talk about the current in inductor, then current in inductor is given by 1 by L, again integration from minus infinity to T, and this will be your V dt. And the current across capacitor is given by I is equal to C dV by dt. Okay, with having these equations of current, voltage across resistor, inductor and capacitor, we can get some properties of these elements. And what could be those properties? Like you can observe in the resistor that in resistor, if you are finding voltage or current, it only depends on the resistor. It is not having any problem with change in current or change in voltage across it. Whether with respect to time, if we change resistor, then accordingly its current will change, its voltage will change. So it doesn't depend on the time, it depends on the value of resistor. Value of resistor, whatever its value, accordingly we will get the voltage. But in case of inductor, suppose if we change time, with respect to time we have to consider what change in current is there. If current is changing too fast, then our voltage will be high, and if current is changing very slow with respect to time, then our voltage will be low. So it means our voltage and current is depending on the time. And what are those dependence? Those dependencies are like, if we suppose, for example, if we change with respect to zero time, if we change, okay, or we can take this equation in frequency domain, and in this frequency domain, this equation can be given by V is equal to L omega into I. And you all know that this frequency, relation of frequency with respect to time, you know that frequency is given by 1 by t. So as if we are considering about time t equal to 0, it means we will be taking frequency at infinite. And if we will taking t is equal to infinite, it means we will be considering f is equal to 0. So in that case, the voltage is given by, voltage across this inductor is given by L into omega times I, and L into omega is nothing but the reactance of this inductor. We had already discussed about reactance multiple times. So this reactance, if we talk about this reactance at t equal to 0, the reactance will be infinite. Reactance of this inductor will be infinite, and if inductance, the reactance is infinite, it means at initial value, at initial time, this inductor will behave as an open circuit, because since the reactance is infinite or reactance is considerable like your resistor. So if resistor is infinite, it means it is going to be an open circuit. So at initial condition, this inductor will behave as an open circuit. And if we talk about at t equal to infinite, at steady state time, at after long time, it will take long time, your frequency will be 0. For t equal to infinite, your frequency will be 0. If f is 0, it means the reactance will become 0. So if reactance will become 0, it means it will behave as a short circuit. So at the infinite time means at the steady state, your inductor behave as a short circuit. And in case of capacitor, we are having just opposite relations. You can observe even from the equations as well. So at t equal to 0, if we take in terms of frequency domain, so this will be c omega times I, c omega times, sorry, v. So or we can write this relation in frequency domain like v is equal to 1 by c omega times I. So from this you can say that your reactance of capacitor is 1 by c omega. 1 by c omega. So now from this relation, we can get, like, if we are talking about initial condition, so at initial stage your frequency will be infinite. So if this is infinite, it means your capacitor will behave as a short circuit. And in case of t equal to infinite, your omega will be 0, and in that case your capacitor will behave as a open circuit. So now we can conclude these two main important relations, and those relations are: at time t equal to 0, your inductor behave as an open circuit and your capacitor behave as a short circuit. But at the steady state, at t equal to infinite, your inductor behave as a short circuit and capacitor behave as a open circuit. If you don't get these relations, don't panic. We will discuss these relations in next slide in little more detail. Let me divide our time domain analysis in two parts. So we will be having time domain analysis in two parts, and those are your transient analysis and steady state analysis, as I was discussing about it. So what is this transient analysis and what is this steady state analysis? Okay, if I'm having a circuit with some connected components, with having components with inductor and capacitor, there must be, if we are talking about transient analysis, then there must be a circuit with having inductor or capacitor, or it could be inductor and capacitor. So there must be an, you can say, memory element. and that memory element could be a inductor, could be a capacitor. So if we are considering this line as our time domain, so if suppose we are having a circuit within a stable condition, and at time t equal to 0, let's make a disturbance in the circuit. So disturbance could be like we can change the value of the resistor, we can change the value of any of the component, we can remove an element from the circuit, we can switch on the circuit. Earlier suppose our switch was off and we can switch it on, or we can make any of the change. If we will make any of the change, our circuit will not be stable anymore. So earlier, before switching the circuit, before making any disturbance in the circuit, your circuit was in the stable state condition, or you can say steady state condition. Steady state condition. And when we'll make the disturbance or when we'll switch it on, after this means your capacitor will may start charging or may start discharging, or similarly your inductor may get start charging or discharging. So after this switching, there will be some transient relation will be there, and that relation will be known as transient analysis. Transient analysis. And after some time, after once we make some disturbance in the circuit, and then after some time we will observe that our circuit again comes to the rest condition, or rest you can say, in again it will come to the steady state condition. So we will be having two kind of responses. One could be your steady state response and one could be your transient response. Our main focus will be on this transient response. Means that after switching the circuit, what will be our response? What will be the voltage across the inductor, or what could be the current across the capacitor? What could be the current across inductor, or what could be the voltage across capacitor? So we will be observing these values within that within this transient region, and we will discuss about what will be the initial conditions, what will be the final conditions in that circuit. Okay, so first we will discuss about the initial and final conditions, then we will come to discuss about the detailed instructions or detailed analysis of the transient analysis. Okay, so now let me take up very small circuits, and we will discuss how we'll get the initial and final conditions of some standard circuits. Okay, so now I have taken a circuit which is having a resistor and an inductor in series, and earlier it was open. The circuit was open, means the battery was not connected with this combination. If it is not connected, it means there is no supply. If there is no supply, there will be no current. Okay, so it means earlier, before switching the circuit, if I'm considering like at time t equal to 0 minus, before just switching the circuit, the current in the circuit or current in the inductor was 0. Okay, then after just switch it off, after just switch it on, is at t equal to 0 plus. As I had earlier told you that what is the initial condition of this inductor? At initial stage, inductor always behave as a open circuit. So as I will switch the circuit, the inductor will behave as an open circuit. Means whatever current over here is, that will be same. There will be no change in current across it. Even this is the property of the inductor, that inductor doesn't allow sudden change across it. That's the most important point of this lecture. That's inductor doesn't allow sudden change across it. Let me repeat it again, that inductor is having a property that it doesn't allow sudden change in current across it. So earlier if the current was at 0 minus, if the current was 0, so at 0 plus this will be also 0. Even whatever changes you are making over here, you are changing the voltage over here, but this current will not change. That current will remain same. So we will get this I is equal to 0 again. So now this is the initial condition. This is the initial condition of the inductor. Initial condition of the inductor. And if we'll talk about the final condition, means at t equal to infinite, at t is equal to infinite, means at the steady state, the inductor is having property like it will behave as a short circuit. So now inductor will behave as a short circuit. This will become a short circuit. Now if this will become a short circuit, what we will get? We will get the current is equal to V by R. Please note down this condition, this initial, and this is your final condition, or you can say steady state condition. Steady state condition or final condition. Why does the inductor not allow any current? No, it's not like any change, any current. It allow current, but it doesn't allow sudden change in current. Okay, sudden change in the sense like, if as you know that your voltage across inductor is like L di by dt. Okay, let me come to this point. L di by dt. So if we'll make a change like at t equal to 0, at t equal to 0, if there will be any change, means at the very small change in current, or at t equal to 0, if there will be any change over here, if there will be any change over here, it means this value, suppose there is a change of 0.1 ampere, for example, and we are taking this current as very small change like t equal to 0. So now this will become infinite. This will become infinite. Means your inductor will vanish. Okay, so this is the property of inductor. Like inductor doesn't allow any change in current if we are taking time change in 0, or you can say if you are talking about sudden change. Sudden means when the dt is 0. When if dt is tends to 0, then this should also be tends to 0. Means it to make this a constant value, or a, you can say, measurable value, this should be there should be no change in current. Okay, infinite reactance. Yes, it can be a type of infinite resistance. That's why it will become open circuited at initial condition. That's correct. Okay, hope you all got this point. This explanation about the RL circuit, that we had discussed about only initial and final condition, and we will take now the similar approach for the circuit again. Okay, now we will take another circuit, and now we will try to understand about this circuit. Okay, now the condition is like, the question is like, earlier it was in the that switch was connected to position 1, and after it it became in a steady state. Now this switch is changed to position 2. Earlier this switch was connected to position 1, and after some time this switch is switched to position 2. So now what will be the condition, and what will be the initial state, what will be the initial condition, and what will be the final condition? So if we talk about the initial sorry, if we talk about the initial condition will be like, we will be talking about t is equal to 0 minus. So first we will discuss about at t equal to 0 minus. So at t equal to 0 minus, the current, can you tell me what will be the current at t equal to 0 minus for this circuit? if I'm taking current over here is I? Can you tell me, quickly tell me, if you got this point? Okay, Monica is saying it should be 0. Anyone else having some different answer? Okay, you all are just copy pasting. You all are just copy paste, copy and paste, copy and paste. You didn't listen the previous thing. Okay, let me go back to the previous slide. Okay, so this was the condition that t equal to infinite, the current was V by R. And in this circuit, what I'm saying that this circuit was in the stable state before switching. Before switching, it was in the stable state. So if it was in the stable state, or you can say it was the steady state condition, then what will be the current? What will be the current at the steady state of the circuit? Still you're saying I. I'm just asking the value of this I. What will be this value of this I? Yes, now someone, yeah, Sinelic comes to the right answer. Yes, obviously it will be V by R, because this was the steady state condition. So earlier the circuit was in the steady state. So at time t equal to 0 minus means just before switching, the current will be V by R. Okay, hope you all got this point. Then can you tell me what will be the current at t equal to 0 plus? Just after switching, and the condition means after switching, this switch will be connected to this position 2. Okay, I can even redraw it. And now this switch is come to in this position. Now the switch is in this position. Now if it is in this position, then what will be the current? Can you tell me quickly what will be the current at this time? Okay, Sainal is saying 0. Vishal Yadav is saying V by R. Okay, no. Okay, again you didn't listen my explanation carefully. What's the property? Property of inductor is it doesn't allow sudden change. As you are saying, if it is 0, it means your current across inductor got changed by V by R to if you will make it 0. If you will make it 0, it means your current got changed by V by R. But it's not the property of inductor. The property of inductor, it doesn't allow any change. Means if the current was this, the current will remain same. Means if we are changing, if at before, because this 0 minus and 0 plus is like just a fraction of time, means you can consider this change, the change in time is 0. So if with change in time 0, current cannot change. So if we are having steady state condition, or if we are just switching the circuit, the current will always remain same. Hope you all got this. Then can you tell me what will be the current at t equal to infinite? At steady state, what t, what will be the current at t equal to 0? Yes, Vishal Yadav is correct. Means at time t equal to infinite, at steady state, you can observe from the circuit like there is no supply. No supply means no voltage, as I have already told you that at steady state this will behave as a short circuit, means inductor will vanish from the circuit. If inductor will not be there, means your circuit will be having no current. So in the steady state we will get 0 current in the circuit. Okay, hope you all got this. Then we will take another circuit and then we again discuss about the initial and final condition of the circuit. Okay, so again in this case, while we will be discussing about capacitor, we will be taking voltage across that capacitor, and if we will discussing about inductor, we will be taking current across the inductor. Okay, so it will, you can even, that's not the fixed condition, means you can discuss about current and voltage about the inductor and about the capacitor, but in general we will be taking if we are having inductor, then we will be finding current, means you know that if we got the current, we can get the voltage. Okay, similarly in the case of capacitor, we will be finding voltage across the capacitor. Okay, so in this case, suppose at before switching at t equal to 0 minus, before just switching, what will be the voltage across the capacitor? I'm talking about voltage across this capacitor. Can you tell me what will be the voltage? Yes, that's correct. Vishal. Monica is also correct. Obviously, because since there was no supply, there will be no voltage. Okay, so what will be the voltage at t is equal to 0 plus? Can you tell me quickly? At 0 plus, again it is going to be 0. That's correct. And at t is equal to infinite, can you tell me what will be the voltage across this capacitor at t is equal to infinite? Voltage across this capacitor at t is equal to infinite means again you that this is switched at t equal to 0. This was switched at t equal to 0. Then what will be the voltage at infinite? Okay, Vishal Yadav is saying V minus IR. Okay, Ankit Viskarma is saying IR. And anyone else having some different answer? Okay, no one having any answer. Okay, let me tell you that the property of capacitor, is at steady state, this capacitor behave as a, earlier I told you, behave as a, can you tell me, open circuit or short circuit? Open circuit. You all got it this? Okay, you all got this. So if at steady state, if your capacitor is open circuited, means there is no current over here. Means if this is gone, means this is open circuit, then there will be no current, means current will be 0. Then what will be voltage across this? Now can you tell me? I think Vishal can, yes, I was expecting answer from Vishal. Yes, because you told me the answer like V minus IR. Now because this capacitor is open circuited, now the voltage across this will become V only, because there is no drop across this R. Voltage drop across this R will become 0. So the total voltage across this capacitor will be V. So voltage, okay, if we are talking about across capacitor, so the voltage across capacitor will become V at steady state, because now that's the condition of the charging of the capacitor. This is just a property of charging of capacitor. Now in this case your capacitor is fully charged, and if capacitor is fully charged, it means it will charge up to the voltage, whatever voltage is applied across it. And this is the condition of your ceiling fan, as we had discussed in the previous lecture. Like if we are having this capacitor, so what will happen, like and even we will see that how this voltage is varying from 0 voltage to this voltage. That will be your transient analysis, and we will discuss in detail about this, so don't worry about that. Okay, so so this is the condition, like capacitor is charging from 0 to V up to from t is equal to 0 to t equal to infinite. I hope now you got this condition. Is there is any doubt to understand this steady state condition of capacitor? Is there is any doubt? Quickly tell me if there is any doubt. Okay, so if there is no doubt, so we can take this again similar circuit to this one, and again let me take this as position 1 and this as position 2, and earlier the switch was connected to position 1, and at t equal to 0, this switch is moved from position 1 to position 2. So now can you tell me the conditions about that t equal to 0 minus? What will be the voltage across capacitor? What will be the voltage at t is equal to 0 plus about this capacitor? And what will be the voltage at t equal to infinite about this, please? So only Vishal is giving me the answer. Why all other are not giving me the answer? Okay, Yes, because that's very simple. Like at t equal to 0 minus, it was in the steady state condition. As in the previous slide, we had discussed that at the steady state, the capacitor voltage will be V. As at steady state, capacitor behave as an open circuit. So if it is an open circuit, your voltage will be equal to this voltage, and there will be no change if we are talking about at 0 plus, means just after switching, as the capacitor is having property that it doesn't allow sudden change in voltage across it. Okay, so you can make this note, like capacitor is having property that capacitor doesn't allow sudden change in voltage across it, as the inductor was having property like inductor doesn't allow sudden change in current across it. Similarly, capacitor is having property that capacitor doesn't allow sudden change in voltage across it, and the explanation will be exactly same. As I had explained about the capacitor. So here the current across this capacitor is given by this C dV by dt. Okay, so if you want the constant current or the current which can be measured, in that case, if we are taking a very small change in time, means if your time is 0, there should no change in voltage. If there will be any change in voltage, it means it will become not measurable or indeterminate. Like it will be the form of 0 by 0. Indeterminate form will be there, and we will not able to measure the current. Okay, so if there will be 0 by 0 form, then this could be a positive, this could be a constant value. If there will be any change, means if there will be some value, suppose 0.1, then this will become infinite. So infinite current will be there. So this is the property of capacitor, that capacitor doesn't allow sudden change in voltage across it. Okay, hope you all got this point, this explanation of why this capacitor doesn't allow change in voltage across it. Okay, so if you got this, so let me go to the next slide and let me summarize